turn it into a fraction. So first I'm going to rewrite the problem. Yeah, I'm going to turn it into a problem in terms of sine and cosine. And it just so happens that this one is really nice, right? Because secant is 1 over cosine, and tangent is sine over cosine. And we have the same denominator, right? So we don't even have to get like a common denominator. It already is a common denominator. So this is just limit x goes to pi over 2 from the left of what? 1 minus sine x on top over cosine x. And now if you do this way, you should get an indeterminate form that we can use L'Hopital's rule on. Let's see. Pi over 2. What's sine of pi over 2? So I'm going to go to the unit circle to remember this. Pi over 2 is straight up, isn't it? What is sine? What's the y coordinate when you're straight up? 1. So this is 1 minus 1 over, what's cosine of pi over 2? So pi over 2 is straight up, 0. It's the x coordinate. So this is 0 over 0 now, isn't it? L'Hopital. See, we were able to convert infinity minus infinity to 0 over 0. So by L'Hopital's rule, I put my little L here with the circle around it. I do derivative of the top, which is just negative cosine x, over the derivative of the bottom, which is minus sine x. The minuses are going to cancel each other out, aren't they? They're going to go away. It's going to be positive. What is cosine of pi over 2? Pi over 2, cosine is 0. Over sine of pi over 2. Sine of pi over 2 is 1. 0 over 1 is just 0. That is 0. Remember, the original problem was infinity minus infinity, right? And what it turns out to be that as you go closer and closer to pi over 2, these two kind of like agree to meet in the middle, all right? And they're like, we'll meet at 0, all right? That's what they do. Doesn't always work that way. Don't ever tell somebody infinity minus infinity is 0. It's an indeterminate form. Every problem is unique. Every problem is different. You actually have to work it out and see what happens. I actually think it was this class that somebody asked me, if we get infinity minus infinity, if the only answers that we could ever get would be infinity or negative infinity. I think someone asked me that in here. I could be wrong. But the answer is no. It is possible to have infinity minus infinity go to a number. And it can go to a number other than 0. It can be like, for some reason, you could have a set of functions that when you take the limit, you get something like 2. It could happen. Just depends on the problem. All right. Now the next one we're going to do, 0 times infinity, is critically important. Because if you can't do this, you won't be able to do the other 3. You have to be able to do 0 times infinity to do the 0 to the 0, the infinity to the 0, and the 1 to the infinity. All right, so let's do one. All right, we'll start with limit x approaches 0 from the right of x ln x. So where is x headed? 0. Okay, so this is headed to 0 times, and then natural log of 0 is undefined. But that's not what we're saying. We're saying what happens as you approach 0 on the natural log function from the right. It goes to negative infinity, right? The natural log function dives down to negative infinity. So this is going to negative infinity. So this right here is this form. Now I didn't put this here. You might want to put this here. This does not matter if it's plus or minus, okay? That doesn't matter. 0 times a big positive number or 0 times a big negative number is still an indeterminate form. Okay, you ready? Here's the critical thing that you do when you see something like this. When you see 0 times an infinity, you're going to grab one of those. There are two factors, right? You see them? X and natural log x. You're going to grab one of them, and you're going to drop it to the denominator. But it has to be the same expression as what you have up here. So watch me do it, and then we'll talk about it. I'm not doing L'Hopital. Just watch. Do you agree that that's the same problem? Yes? Yeah, because if I write 1 over x on the bottom, you could say, oh, just flip it up, right? And it would become an x up here, wouldn't it? You all agree? That's the same exact problem, just rewritten a different way. But by me doing that, let's see what we actually get if I take the limit now. And I want you to look at it as this over this now. So what happens to the numerator as x goes to 0? What does natural log do? Goes to negative infinity. We just said that. So the top goes to negative infinity. Now the bottom. 1 over 0, right? Fixed over 0. Fixed over 0 goes to either infinity, negative infinity, or does not exist. The numerator, though, is always positive. The denominator is approaching 0. From the right, which means it's always positive, positive over positive would be positive. So the denominator is headed to positive infinity. Do you get that? No questions? Sure? Now does it look like I can use L'Hopital? Yes, I can. That's clever, isn't it? Isn't that kind of clever? It works, right? Okay. All right, so when I take the derivative of the top, what do I get? 1 over x. Derivative of the bottom, be careful. What's derivative of 1 over x?
It's x to the negative 1.
1 over x is the same as, I'm trying to take derivative of this, is x to the negative 1, right? I'm trying to take its derivative. So negative 1 x to the negative 2? Negative 1 x to the negative 2, or negative 1 over x squared. Can I write it that way? Can I write that like that? All right with you? Flip it now. Fraction over fraction, flip it. Don't go giving me L'Hopital again. Let's clean it up first. This equals, I just said don't do L'Hopital. Limit x goes to 0 from the right. When I flip this, it's 1 over x times x squared over negative 1, just flipping. One of the x's cancel. One of the x's cancel. You just get x over negative 1. So limit as x goes to 0 from the right of x over negative 1. Let x go to 0. 0. 0 over negative 1 is 0. Your answer is 0. Bam.
A lot of zeros.
Yeah. So that limit approaches 0. You all get it? Now, I said that if you see 0 times infinity, you're going to do what?
You're going to make it a fraction.
Okay. Said you're going to grab one of the two, right? And you're going to drop it down. I grabbed the x and dropped it. I could have grabbed the natural log. I'm going to show you that now, and then you're going to see why the better choice was x. All right? So I'm going to do this problem over again. We have the same thing happening. I'm going to leave the x on top, and when I drop the natural log, how do I have to write it on the bottom? 1 over ln x. That's the way I have to write it. And now if I let x go to 0, I'm looking at these separately. I have this, and then I have this whole fraction, right? The top goes to what? 0. The bottom goes to, careful, not 1 over 0, careful. Natural log of 0 is going where? Natural log of 0 is going to negative infinity. 1 over negative infinity. Fixed over something infinite. 0. Fixed over something that's getting big. I understand it's big and negative, but it doesn't matter. 1 over a big negative number, 1 over a big positive number. It's still a small number. So the bottom is headed to 0 also. Got it? So can I use L'Hopital? Yes. But do I really want to take the derivative of the top and bottom? The top I think you're not that concerned about, right? But look at the bottom. When I do L'Hopital here, everyone's like, oh, the derivative of x is 1. This is beautiful, right? But then what about the derivative of natural log x? You have to use quotient rule. You have to use the quotient rule. Or if you don't want to do that, you have to rewrite it as natural log x to the negative 1 and then do the derivative, which is chain rule. So what would you like? Would you like me to do quotient rule on this or chain rule on that? Chain rule? Okay, I'm going to take derivative of this. Derivative of this would be negative 1 comes out times what? This to the what? Natural log x to the negative 2 times derivative of what's inside? 1 over x. Do you see the chain rule on that? And now we have to clean that up. Okay, so let me clean it up. Limit x goes to 0 from the right. 1 over, okay. I'm going to put this negative 1 as being on top. This is going to drop down, so it's going to be ln x, right, squared. And then this x is going to be down there with it, right? And what happens if x goes to 0? Well, I can flip that, can't I? Can I flip that? Like this is a fraction over fraction. I just flip the whole thing over. Okay. And I would have a negative, so it'll be negative. When that flips up, I'm just going to get x ln x squared. Do y'all see that flip? We're happy? No, we're not happy. X goes to 0. Where does that go? 0. Natural log of 0? Negative infinity, squared, infinity. Guess where we are? Right back to where we were. We're at 0 infinity again. Not only that, look, we had x natural log x. By picking the wrong one to drop, I now have x natural log x squared. It's actually more complicated now than it was before. So when you're trying to choose which one to drop, think about whatever you drop, whichever one you drop is going to become 1 over that, right? Do you really want to take the derivative of that? That's what you have to ask yourself. That's why I picked the 1. That's why I picked the x. When I dropped the x, it became 1 over x. I'm okay with taking derivative of 1 over x. That is not as intimidating or as bad as this turned out to be. Got it? All right, let's do another one. It's so sad. The book only gives one example of that, and that's it. They move on. But I'll just make up something else. How about... Okay. Limit x goes to infinity of x sine of 1 over x. And you know what? Let's make this in here 4 over x. Try and stop you from cheating on this problem. Let's let x go to infinity. You have infinity times 4 over infinity goes to 0, right? Sine of 0 is 0. So this is infinity times 0. And that's not good. That's an indeterminate form. And so we got to do something. Anytime you see 0 times infinity, you have to pick one and drop it. So which one would you like to pick and drop? The x, right? That seemed like the natural candidate here. So this can turn into sine of 4 over x over what? 1 over x. Double check it. If you did it right, you should now have either 0 over 0 or infinity over infinity. One of the two you should have. So x goes to infinity, 4 over infinity is 0, sine of 0 is 0. So I get 0 on top. I'm just going to put it down here. 0 on top is the form I'm getting. 1 over infinity goes to 0, 0 over 0. Check. L'Hopital. L'Hopital. What do you got up top? Cosine of 4 over x. Agreed. I heard times. Times.
To the negative 2.
Negative 4 to the negative 2? What?
Negative 4x.
X to the negative 2. All right, so look. Look at this 4. This is 4 times 1 over x, right? That's what 4 over x means. Right? That's what that is? 4 is a number, a constant attached to a function. It's going to come for the ride. What's the derivative of 1 over x? We already did this, all right? Right? We did? Do you remember I told you everyone here should know what the derivative of x, root x is? Like 1 over 2 root x? The derivative of 1 over x is another one of those ones that comes up a lot. So everyone here should know the derivative of 1 over x is just negative 1 over x squared. Because it happens enough that if you just have that kind of memorized, it'll serve you well. You understand how I'm getting this, right? Rewrite this as x in negative 1, then do power rule. All right, so that means I'll have a 4 that comes along for the ride, and then next to it, negative 1 over x squared, which is the same as negative 4 over x squared. With me? Questions? Over? Over? Negative 1 over x squared. Hey, 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 hey. That's wonderful. That's awesome. Right? That's a great thing that just happened there, right? Isn't that awesome? What do we get? If these are gone, I can take a limit now. Let x go to infinity. 4 over infinity, 0. Cosine of 0, 1 times 4, 4. The limit is 4. That thing was heading to 4. The further that x goes out, if you graph these two functions, it'll head to 4. All right. I think we're ready. I think we're ready to move on to these three. All right. And this will probably be the last problem I do for the day, because we got about, what, 20 minutes or so? They're not that long, but I mean, this is an important example. So I'm going to take my time. Limit x goes to infinity of 1 plus 1 over x to the x. I've had a habit in the past to put a problem like that on the test. And when people don't get it, I usually squeeze one tear right here. It just like comes out and I'm just sad.
What, you feel like you failed?
Well, because even when I present it, I tell them how important it is, and then on the test they still can't do it. So I just showed you this, right? I told you it was E? Yeah. Okay, so let's see how we're going to do this. You can memorize that it's E, yes, but if I ask you to show what this limit is, then you'll have to. So let's first appreciate what is happening. Take the limit. We know that this is 1 to the infinity, right? We talked about that. We know that that's an indeterminate form. We can't just grab something and drop it to the bottom and create the 0 over 0 or infinity over infinity like we just did, because there's nothing to grab. There's not a product of two things. This is something, right, raised to something. How do you mean combine? Inside, you could get a common denominator, but that's still not going to allow you to deal with the x that's on the outside, which is going to infinity. No matter what you do on the inside's going to still go to 1, no matter what. Like if you were to put them together, this is what you get if you put them together. And if you said, hey, what happens is x goes to infinity on this, you have infinity over infinity. So let's say you do L'Hopital on that, you get 1 over 1. And then you're going to say the inside goes to 1. But we already know that. The inside goes to 1. The problem is the fact that the exponent goes to infinity. So let's see. Do you remember what we did? There was another type of differentiation. Think back. Differentiation that we used that I showed to you like a class or two ago. Logarithmic differentiation. And what we were doing in that was I would give you something like y equals, let's say, x to the x, and I asked you to find the derivative, right? Find y prime. And what you did is you took log on both sides. Now this is not, I'm not giving you a function asking you for its derivative. The reason I'm asking you to remember this is because having logs, introducing logs into problems allows us to drop powers out, doesn't it? That's what I'm going to do here. I'm going to introduce a log. But to do it, I actually have to create an equation first. So just, if that's our problem, what I'm going to do to start is I'm going to rewrite this like this. All I'm doing is I've decided to call this thing that I'm looking for y. I could have called it m, I could have called it p, I could have called it c, I could have called it anything except x, because x is over there. But I can call that whatever I want, right? So everyone, I want to know what y is, right? That's what I want to know. What's y? But now that I've created an equation, I can do things to both sides of the equation and just maintain the equality down both sides. So let me take the natural log on both sides of this equation. The natural log of y is equal to the natural log of this entire thing. Now I heard 1 over y. I think you wanted to take the derivative.
Oh, crap, yeah.
We're not going to take a derivative, all right? So the only thing that's similar between this and logarithmic differentiation, the only thing that they have in common is the fact that we're doing log on both sides. After that, they're completely different, what we're going to do. Do you agree with that? I can do the natural log on both sides. Now this next step is one of these steps you have to kind of take on faith, but it's earlier in the book. Its property of logarithms, or in limits, is that if you want to take the natural log of a limit of something, you can actually put the natural log past the limit. So your next line could look like this. And notice I'm keeping the left side and right side the whole time. I'm going to work them down left and right together. This limit, as x goes to infinity, of the natural log of 1 plus 1 over x to the x. So this was in properties of logs. Properties of limits back in the first chapter of limits. It said that if you're taking the limit, this is what it was. If you're taking the limit of a function, a composition of functions, that you could pass the limit inside and make this f of the limit as x approaches whatever, g of x. So you could pass it through the function. You have to believe that this works for the natural log. Okay? You have to take that on, kind of on faith, but it was in the limit laws. And that step right there allows me to do everything I need. Do you see what I'm going to do? I'm going to drop the x out. Okay, so let me drop the x out. If I drop that x out, it goes in front of the natural log. Bam. There we go. Now, again, I'm not taking a derivative. I'm just going to now look at what limit I have, because I've done something to it. Let's let x go to infinity and see what we get. As x goes to infinity, this goes to infinity times, now take your time here, 1 over infinity, 0, 1 plus 0, 1. This is approaching 1. We kind of knew that already. This is approaching 1, but now it's natural log of 1. What's the natural log of 1? 0. Ah, now we have infinity times 0. How do you deal with infinity times 0? You pick one and you drop it. Which one would you like to pick? X. Yeah, I think it's obvious to pick the x and drop it. So my next line is going to be this. Natural log y equals limit x goes to infinity. I've not taken a limit yet, right? I have not actually done a limit. I have not done L'Hopital. Everything up to this point has just been rearranging, manipulating. I take that x, I drop down as 1 over x. I'll check one last time to make sure that this is set up for L'Hopital. I'm going to compare this and this one. The top one we already know went to 0, right? The bottom one, 1 over x, now goes to 0 because x is going to infinity. So I have 0 over 0. L'Hopital. So this is the way I'll write it so that everyone knows I used L'Hopital. I'm going to put equals here. I'm going to put my L'Hopital above the equal sign. And then the limit. X is going to go to infinity. The derivative of the top. I know the derivative of the top looks bad, but it's not that bad. What's the derivative of natural log of anything? 1 over itself. 1 over whatever's in there, right? So I'm going to put 1 over whatever's in there. Agreed? That's derivative of natural log of something. Chain rule says now go inside that natural log and take the derivative. What's the derivative of 1? 0. So I'm going to say times, this would be 0. I don't need to write the 0, do I? Okay. So it'd be times, actually I won't need the parentheses because I'm only going to have one term here. So what will that one term here be? Derivative of that 0, derivative of that, negative 1 over x squared. We just said that's important if you just remember that one. Are we done taking derivative on top? Yeah. Yes. Over, right, over, derivative of the bottom. Negative 1 over x squared again. And is that good? Happy to see that? Those two cancel. And what you're left with is the natural log of y equals the limit as x goes to infinity of 1 over 1 plus 1 over x. And now I'm ready to let x go to infinity. So 1 over infinity goes to 0. 1 plus 0 is 1. 1 over 1 is 1. So natural log of y is 1. Wait, I thought I said the answer was supposed to be e. Oh, well, wait a minute. We didn't want to know what natural log of y was. We wanted to know what y was, right? What I can tell you is that natural log of y is 1. So now let's undo the natural log now. How do we undo natural log? With e. So if I do e natural log y, that should be equal to e to this side, right? E to this side should be equal to e to this side. E to the natural log of y should just be, e to the natural log of y should just be, e to the natural log of y should just be y, and then equals e to the 1, which is just e, right? So y is e.
Do we have to do all that? We can't just put e.
No. Unfortunately, no.
Okay, so you just proved this, right? In other words,
I kind of did. Kind of. Y'all okay with that? That only took about 10 minutes, and we still have 10 minutes. Okay, what about this? y is, not y, sorry. Limit, I'm going to work through this one kind of quick because it's going to be very similar to what we just did. Let's see, I'm going to see if you can follow me on this. I'm going to make this n goes to infinity instead of x goes to infinity. I'm going to put 1 plus 1 over x to the over n to the n. Does that look kind of familiar, like similar to what we just did? Yeah. If you replace all your x's that we had in the previous problem with n's, I would have the same thing, right? But instead of a 1, I put an x there, all right? So see if you follow me on this. What happens as n goes to infinity? What's some number, and I'm going to tell you right now, x is fixed, okay? Fixed number over infinity goes to 0. 1 plus 0 should get close to 1. So this looks like 1 raised to the infinity. All right, when I see that, I'm going to do exactly what I just did. Natural log on both sides. Got it? Well, I need to call this y. Let's call that y, natural log on both sides. I'm also going to pass the limit through, or pass the natural log through. I'm moving fast because I want to get to something here. That's exactly the same thing we just did. I called this y, I took natural log on both sides, I passed the natural log past the limit. Now I'm going to drop what out? The n is going to drop out. Natural log y equals limit n goes to infinity of n times natural log of 1 plus x over n. Drop the n down. Natural log y equals limit n goes to infinity of natural log of 1 plus x over n over 1 over n. That will give you 0 over 0 still. You can use L'Hopital. Okay, this is the part we have to be a little careful with. What is the derivative of natural log of something? 1 over that something times derivative of what's in here. So pay attention here. Derivative of 1 is 0. Derivative of x over n with respect to n. N is the thing we're differentiating with respect to. So I want you to look at x over n as being x times 1 over n, where x is a constant. So it comes for the ride, and we get... I couldn't hear you. X times... How about, can I do negative 1 over n squared? So the x is going to come for the ride. Then I'm taking derivative of 1 over n, which is negative 1 over n squared. Over, all of this over, negative 1 over n squared. Do you see how similar this is to the one we just did? The 1 over n squareds cancel. And now at this point, I want you to let n go to infinity. Let n go to infinity. What happens? X over infinity, 0, 1 plus 0, 1, 1 over 1, 1 times x. See, x isn't going to infinity, right? So this is just going to turn into a 1, and that's going to just be x. Understand? And so you get what? Natural log of y equals... Natural log of y equals what? Natural log of y equals what? X. But I wanted to know what y was. So now e, both sides. So y is what? E to the x. What? What does this mean? Hold on. What did we just prove? What did we just prove? We just proved that if you take the limit as n goes to infinity of 1 plus x over n to the n, that this is actually the definition of the exponential function e to the x. Now e to the first power, right, is just replace that with 1. And do you remember I told you to do that on your calculator? We did it, didn't we? We did, I told you to make like a table 1 plus 1 over n, or no, x to the x, and we plugged in different values of x, and it got closer and closer to what? 2.718. Well, if you want to know what let's say e to the 4th power is, then you would just go in here and just replace that with a 4, and then start going in your calculator and go bigger and bigger n's, and that would get you closer and closer e to the 4th power. Okay, we're going to do more of this, all right? It's not, we're not done talking about this. Does anyone have the schedule with them? Yeah. Are we supposed to finish L'Hopital today or next class? Is it next class?
Next class.
Okay, so we are going to spend more time on L'Hopital next time, maybe the first half of the class. And we don't have a whole lot more to do. I just need to show you some more examples so you can see where things can get a little messy. And then we're going to start 4-1. This section, I did all the homework on video already. I think it took me like 2 hours to do. It's a lot of homework. I would start doing. You could theoretically do them all now. You've seen every technique. What you haven't seen are these two types, right? But you approach them the exact same way as this type. You come in with natural logs, you drop, and when you drop, it's going to become either infinity over infinity or 0 over 0. So you have everything as far as the tools. It's just, have you seen enough examples yet to do them all? So start with your homework, come in with questions, have a good day.